Okay, so today we're going to be starting our thermochemistry unit. Now, thermochemistry has to do with energy. Okay, now there's different types of energy. And again, you do not need to write all these definitions down. I'll tell you guys what's important and what's not. But there are two main types of energy. The first is kinetic energy, and you don't need to write this down yet. Kinetic energy is energy in motion. Okay, so when you're driving your car, and it's going and it has that energy of movement, that's kinetic energy. But in this course, we'll be talking more about potential energy. You guys don't need to write this down. And it's stored energy, energy that is stored but is not yet released. Okay, now specifically, and make sure you guys write this down right here, we're going to be talking about chemical potential energy. Okay, and chemical potential energy is the energy that is stored in the chemical bonds of a molecule. So last unit, we learned how to draw these molecule structures, right? Where the bonds go between elements. Well, those bonds contain energy. And by breaking those bonds and making new molecules, we can release energy. And that's the type of energy we will be talking about in this unit, okay? So I'll give you guys a minute. Yeah, make sure you write this one down here. I'll give you guys a minute to copy it down. Okay, but chemical potential energy is energy that's stored in the bonds of a molecule. Okay, there's two important things that we'll talk about, and you guys are familiar with these words, but chemistry, they have a kind of specific definition. And you guys don't need to write this part yet, but the first thing we're going to talk a lot about is temperature. Okay, and we know what temperature is, but if we are very specific about what temperature is, everything is made out of molecules and atoms, right? And so all of them are kind of like vibrating. They're moving around. Now, depending on how much they move, that tells you what temperature they're at. And so I want you guys to write this part down. But if you have something that is considered, right, higher temperature, okay, if you have something that's high temperature, there is more, obviously, energy. Okay, make sure you write this part down. You don't need to write the definition of temperature, but just make sure you write this part. Okay, if something is a higher temperature, that means there is more energy. Okay. So if you heat up something in the microwave or you heat something up in the oven, what you're basically doing is you're putting energy into that object and you're making the molecules move faster. They're vibrating faster. And obviously, if something is low temperature, it's going to have less energy, okay? So keep that in mind because that'll be helpful for what the problems that we do today, but also when we go further into the unit, this basic concept will help you guys figure things out. There's a lot of common sense in this unit. Okay, so that's temperature. It's how fast the molecules are moving. And if you got something that's high temperature, they have more movement, right? More kinetic energy. If you have a lower temperature, they have less movement, which is less kinetic energy. All right, so we got one last definition before we go into the actual problems for today. So temperature will help us understand the next concept, and the next concept is heat. Now, I know that in our everyday lives, we kind of use these words synonymously, but heat also has a specific definition in chemistry as well. And you guys don't need to write the definition down. But heat, it has to do with energy going from one object to another, okay? Now, this part you do need to write down. Heat always goes from something that is a higher temperature to something that is a lower temperature, okay? So basically, the hotter object gives energy to the colder object. Okay, so whatever is hotter, if it touches something that's cooler, it gives thermal energy, it gives energy to that. And that's what we call heat. It's when energy goes from something to another thing. Okay. All right, so for our problems today, we're going to be drawing these things called heat diagrams. And I'll show you guys how to do that. It's pretty simple. Just keep in mind, energy always goes from the hotter object to the cooler object, okay? So for number one, we got an ice cube sitting on a table on a hot day, okay? So we're going to draw that, okay? And you guys don't need to make it very pretty or anything like that. You guys obviously know I'm not a good artist, so we got a table, okay? And then we're going to draw an ice cube on it. And then we got the sun just to show that it's a hot day. Okay. All right, and what we're going to do is we're just going to draw with arrows which way the heat is flowing. Now, we learned earlier that heat flows from the hotter object, right? And it goes to the cooler one, okay? So before we do that, let's just think about what is inside of this scenario. So obviously we're looking at the ice cube, but what is the ice cube in contact with? What is the ice cube touching? Yeah, the table is one of them, right? The ice cube is touching the table, but what else is it touching? The air, right? There's air molecules around it. So let's draw these air molecules around it. And I'm gonna label that air. Good. Okay, so the two things that the ice cube is touching is the table and the air. Okay. And all we got to figure out is energy gonna go from the air and the table into the ice cube, or is energy gonna go from the ice cube to the air? Okay, we just said it goes from the hotter to the cooler. So what is hotter, the air and the table or the ice cube? Yeah, obviously the air is going to be warmer. The table is going to be warmer than the ice cube. And so if we draw the heat flow, we just need to draw arrows going from the air and the table into the ice cube just to show that energy is going into the cooler object. Okay. Yeah, that's pretty much it. Okay, that's how you draw a heat diagram. You just need to figure out what is cooler, and energy goes from the hotter to the cooler. So in chemistry, cold is actually not a real thing. Hot is a real thing because hot describes how much the molecules are moving, but there's no such thing as cold. We just have more hot and less hot, and that's how we're going to be looking at things. Okay. All right. Do you guys think you could do one on your own? Okay. Hopefully it's not too bad. All right. And your drawings don't need to be super detailed, as long as you can make it as simple as you like, as long as you get the point across. Okay. So I want you guys to try number 2. Okay, I don't have a coffee on me right now, but let's say I have a cup of coffee on my desk. I want you guys to draw a heat diagram demonstrating which way the energy is flowing. Okay. Okay, so we got a cup of coffee, so I'm gonna draw a cup right here. And then we got some coffee in it. Okay. And then it is sitting on a desk again. Okay, and we just need to figure out which way the heat is going to flow. So same thing as before. The two things that the coffee is in contact with is going to be the table. And there's also some air that's in contact with the coffee, right? Now, if you wanted to say the mug, yeah, you can do the mug as well. Okay, but as long as you got the air, that's pretty much the important part, okay? Because most of the energy is going to go into the air. Okay, so compared to the things that it's in contact with, is the coffee hotter or cooler? Yeah, obviously, hopefully it's hotter, right? And so energy is going to go from the coffee into the air. It's going to go into the mug, and it's going to go kind of into the table. It has to go through the mug first, but it's going to mostly go into the air, okay? And this is the reason why if you have like a hot cup of coffee, it's going to cool down over time. It's going to give the energy to the air around it mostly. Okay. All right. Any questions? Yeah.
You know, tinfoil or like, well, like things like
Mm-hmm.
like, does it like not want to go through this much, or like?
Yeah, so we're going to talk about that later, but the tinfoil insulates it, so it keeps the heat like trapped in there. Yeah, because if you wrap it in tinfoil, air is not going to go out of the foil, right? And so it just heats up the air and just stays in contact with each other. Yeah, great question. All right, so I know that we haven't really looked at chemistry yet. I promise next time we meet, we are going to do this with chemistry. But what we've been looking at is the introduction to thermochemistry. And you guys don't need to write this down, but thermochemistry is just a study of how energy changes because of chemical reactions. So the reactions that we look at this unit, they are reactions where you mix two chemicals together or two or more, and it's actually going to make things hotter or colder. Okay. Now, before we go into the last part for today, we're going to do two last definitions. When we are looking at these thermochemistry things, it's very important that we define these two things, and make sure you write both of them down. We always need to define what the system is, and the system is very simple. It's just what we're looking at. Okay. And typically in this unit, it's going to be the chemical reaction. The chemical reaction is going to be your system, and the surroundings is just what is around your system. Okay, and we kind of did this in the heat diagrams. We looked at something specific like the ice cube or the coffee, and then the surroundings is just whatever is around those things. Okay, so going forward, it's very important that we define what the system is, what the surroundings are, because it'll lead into this next part right here, and I'll describe that in a second. Okay, so the reason why it's important to define the system and the surroundings is because there are two different types of chemical reactions. The first type is this one right here, and it's called exothermic. Now, exo means outside, and so exothermic reactions are where the chemical reaction gives off energy to its surroundings. Okay, so I want you guys to write this term down, exothermic, and we're going to write some definitions for it. Okay, there's two things that are important about exothermic. Okay, first, exothermic reactions, they release energy. Okay, so they give energy to the surroundings. And so when we have an exothermic reactions, like let's say that you are touching an exothermic reaction, it's going to feel hot. Okay, and the reason why is because the chemicals are going to mix and they're going to release energy to the things around it. So if you're touching it, it is releasing energy into you, so it's going to feel hotter. Okay, so that's the first type of chemical reaction that we're going to look at. Okay, it's where they release energy and it's going to feel hot. Okay, a good example of this is if you have like a hand warmer. If you guys have used a hand warmer before, you shake it up, it's going to cause the chemicals inside to mix. And what they're doing is they're releasing energy, and that's why it feels warm. Okay. Another good example is a bomb, right? You ignite a bomb, it's going to release a lot of energy, a lot more than a hand warmer. But that's pretty much the same concept. It's where the chemical reaction releases energy. All right, the second type of reaction is called endothermic. Now, endo means inside, and you can probably tell what it's going to be like. But an endothermic reaction is where the chemical reaction absorbs energy. Okay, so some chemical reactions are the opposite of releasing energy. Chemicals mix together and they start taking energy from their surroundings. And so if you touched an endothermic reaction, it would take the energy from your hand. And so to you, it's going to feel cold. Okay, so this is how chemical ice packs, or if you use like biofreeze or something like that, that's the reason why they feel cold. It's because chemicals react together and then they take away basically your thermal energy. So they're stealing energy from you. And so that's why it feels cold. So those are exothermic and endothermic reactions. And in order to define these two things, we need to determine what the system and surroundings are. We're going to talk about that in just a second, but make sure you guys copy these definitions, and then we'll go into the last set of practice problems for today. All right, so the first problem we're going to look at, and this is pretty much what you'll be doing on your assignment today, is we're going to be doing the same thing as before. We're going to draw the heat diagram, but this time we have to determine if the process is exothermic or endothermic, okay? So I'm going to do one with you guys, and I'll have you guys try some on your own. The first problem we're going to do together, we got an ice cream cone, so let's draw an ice cream cone. Okay. And then it is melting, okay? So this is my ice cream cone, and it's a hot day, so it's melting. melting. All right, so what is the ice cream cone in contact with? The air, right? So we're going to draw some air molecules around it again. And it's a hot day. Okay, so let's determine the heat flow, okay? So if the ice cream cone is melting, now is the ice cream cone cooler or hotter than the air around it? Yeah, it's obviously cooler, right? So is it going to be absorbing energy or releasing energy? It's going to be absorbing energy. Remember, it goes from hot to cold, okay? So just make sure you jot that down if you were unsure about that. Heat always goes from hot to cold. That means the air is warmer, and so the air is going to be giving energy into the ice cream cone, okay? So that's pretty much what we did in the previous examples. Now, we're going to determine if this is exothermic or endothermic, okay? Now, it tells us the ice cream cone is the system. So this right here is the system. And we just need to determine, is the system absorbing energy or releasing energy? Okay. We just said, since it's colder, it is absorbing energy, right? Okay. And so what type of reaction absorbs energy? Endo or exo? Endo. Yeah. So this is going to be an example of an endothermic process. Okay. And that's it. That's how you determine endo and exo. You just need to look at where the energy is flowing. You look at the system. Is energy going into the system or out of the system? And that's how you determine endo and exo. All right. All right. Do you guys think you try one on your own? All right. Let's try one on your own. Okay. So we got this. We have these two right here. And I want you guys to try this with the person around you. I'll give you guys about 3 minutes. See if you guys can draw the heat flow and determine if it is endo or exo. Okay, so take about 3 minutes. Okay, so if we take a look at number 4, we got a firework exploding in the air at the worst place on Earth. Okay, got Disneyland. And so first we need to look at whether or not something is hot or cold. Okay, so the firework is surrounded by air molecules, right? So we're going to draw some air molecules around it. Okay, and then we just need to figure out what is hotter, the firework or the air. So which one do you think is hotter? Yeah, obviously the firework, right? General rule of thumb, if something explodes or blows up, it's probably hotter than what it's around. And so the firework is hotter, so the firework is going to give energy to the system. So energy is going to go from the firework into the air around it. Okay, everybody good with that so far? Okay, makes sense because the air is, when you go to Disneyland, it's like what, 65 degrees when they blow up the firework, so it's colder. Okay, so here the air is the system. Now, is the air absorbing energy or releasing energy? Absorbing, because the firework is hotter, so the firework is giving energy into the air. Okay, so we're looking at the air, so the air is absorbing energy, right? And so in this case, this is going to be endothermic because we are looking at the air. Now, if we said that the firework was the system, this is exo. Okay, so if the firework is the system, this is an exothermic reaction because the firework is releasing energy. But since we said the air is the system, the air is absorbing energy, so it's endothermic, okay? So just keep that in mind. That's why it's important to know what the system is, because that's the thing that we are looking at specifically. All right, any questions on 4? I guess that was kind of a trickier question. Okay, let's look at 5. So, fire is burning in a campsite. So the fire is obviously surrounded by more air. I guess you can see a general trend here with these problems. It's all about air. Okay, now, obviously the fire is hotter than the air. So the fire is giving energy into the air around it. This time, the system is the fire. Okay, and the fire is releasing energy. So this is an example of an exothermic process. Okay. And that's it. That's how we can determine exo and endo. Again, always look at the system. Is it hotter or colder? And that'll tell you if it is absorbing or releasing energy. Okay.